So now let's consider wave reflection. And we'll illustrate it with transverse waves because it's easiest to graphically illustrate. And to understand reflection, we'll consider two very distinct types. First, when one end is fixed. So here we have a pulse on a medium, say a string or a spring or whatever, and it hits a fixed boundary. Namely, what it's attached to, it's rigidly attached to. So that's what it means by fixed. The end is not free to move. This pulse is traveling along the medium. It hits the barrier, and here's what you should see happen. It returns, a return pulse. And if you notice the characteristics of the return pulse, I made it a little asymmetrical so you can see what happens. That leading edge that hits here comes off first, so it's the leading edge going the other way. And basically, we have an inverted orientation. It flips around to the other side. But it's not exactly a mirror image either. Okay, so that's what it looks like. The same pulse, but upside down and going the other way. Now, if we do the same thing with a free end, namely, this time, we're going to allow the end of the medium to move freely when the disturbance gets there. So when the disturbance gets there, it can whop that medium upward, which it's going to try and do. What's the effect of that? Well, the effect is as seen here. This is ideal. In reality, it's never perfect, but the return orientation is right side up or erect. And again, you see the leading edge here is the leading edge on the return. So no change in the wavelength. In other words, the wavelength has stayed the same. No change in the amplitude, how tall, how much of a disturbance there is from the equilibrium position, that amplitude. So we just considered what happens when the wave hits a rigid barrier or an open barrier, so to speak, a free end. What about if it's somewhere in between? So we're going to have the pulse enter a different medium, so it's got a different density and actually speed, it turns out. Okay, that's what we're going to find out. So it's made of something else. There's a lot of ways you can change the medium itself. So there's these different speeds along the mediums. We're going to go from a fast medium to a slow medium. You can think of that as a less dense to a more dense medium. That's often the way it is. So in the before situation, all right, here's a pulse coming down a fast medium, and it hits this heavier, denser, slower medium. So let's look to see what happens after it hits this. Does it make a disturbance in this slower medium? Well, yes, it will. Will some get reflected? You can think of this heavier medium as kind of like a rigid barrier, a fixed end, but not completely because it's not fixed, it's just heavier. So that won't surprise you to see what the result is. It encounters it, and I'm going to show the pulses that result. So this is reflected, and it's like a rigid or a fixed end, it's inverted. Notice it's inverted, and the leading edge and leading edge again, but there is something that's different. Okay, inverted, that's not different, but it's less amplitude. Some of the amplitude or energy has not all reflected. The energy is not all reflected. That's another way to say it. And it's also the same wavelength. Some of that wave energy, the pulse energy, was transmitted into the slow medium, and the slow medium shows a pulse as well. The disturbance in real time is like the same, but in that amount of time it doesn't make the slower medium move as far. So you have not only a smaller amplitude than the original, just like this one is less. They're both less, but it's a smaller wavelength as well. Smaller wavelength because the amount of time for this disturbance to pass along this fast medium, it's the same time it has here, but it's going slower, so it's a smaller medium. Does that make sense? Hope so. So there it is. And now what about slow to fast? Slow to fast, kind of reversing the roles. We have a slow medium. There's the pulse. It's coming. It's going to hit the fast medium. And see what happens. I'm going to show what happens after the fact. Well, when it hits this, it feels a little bit like a free end. A free end. And how did the free end reflect back? If you look back, you'll remember, oh, the free end reflects back erect. So it's not going to surprise you that there it is, erect. But notice, even though it's erect, or right side up, it is of a smaller amplitude. Okay. Then the fast medium, boom, look at that. Okay, so some of that pulse gets transferred to the fast medium. Wow, what happened to that? Well, again, it's the same, the disturbance time that is indicative here in the slow medium is the time during which the fast medium is disturbed. The fast medium travels. That disturbance is like stretched out because it's a faster medium, and at the same time it corresponds to a larger distance. So it's a larger wavelength. And the amplitude is a little bit indeterminate, but really what it comes down to is probably less. But the total amount of energy in this pulse is split between these two. And as long as the sum total is the same. In real life, of course, it's going to be less because there's losses, but the total energy would end up being the same. We haven't talked about wave energy particularly yet, but just from a conceptual point of view for the time being. So there you go. All right, I'm going to throw this summary in here about what determines the wave speed. If you're taking my class, you'll have investigated this yourself. I could also demonstrate it in the room. And basically the idea is that, we can test this by causing a disturbance, a pulse in the medium, and the pulse travels across the room, and we're going to just time it. How long does it take for the pulse to go across? So it's really easy to do. And so you do various tests, and what are the results? So here I'm just going to summarize the results for you. So the amplitude is A, the wavelength is lambda, and the time is t. There's our standardized pulse. It's kind of like our baseline pulse of the wavelength and amplitude. Now I'm going to increase the amplitude. Notice the wavelength has stayed the same amount, but the amplitude goes up. You make a bigger pulse and you time it across that same distance, and the time is same. All right, let's decrease the amplitude, make it less, and send that smaller pulse down, and it takes the same amount of time. Let's increase the wavelength. So now it's the same amplitude as original, but the wavelength is bigger. So the pulse disturbance was slower, okay? And it broadened the pulse. Time to get across the room, the same. Is this getting boring? We got other things we can do. We can decrease the wavelength, making the frequency go up if you were doing a continuous wave. So, same height, but shorter. A little snappier pulse. The same time. We do combinations of this. First combination I'll do is, how about the lambda, the wavelength goes up. Look at that long wavelength. The amplitude down. Boop, little wide squatty thing, okay? And same time. How about kind of the flip side? The wavelength go down, so it's a short wavelength, but large amplitude. Survey said the same. What are the conclusions that we can draw from all these different things? In other words, what determines wave speed? Does it depend on the amplitude, the wavelength, the frequency? Well, from what we see is that the wave motion does not depend on the amplitude. And it does not depend on the wavelength. So it doesn't depend on the frequency or the period either. Only depends on one thing, and that is the medium in which it finds itself. If you don't change the medium, you don't change the speed. And that will conclude this little lesson.